Looks like we can get going. Welcome back, folks. So we're about to jump back to section 3.8, and we're coming up to another pivotal week. We have exam 2 when we return on Monday's class. So exam 2 is only going to go up to section 3.7. Those were the word problems we saw in the prior assignment, but I can't put anything really major on there since it is a timed exam. Like before, we have our sample exam problems posted here. And this weekend is definitely pivotal. I'll be available on the email if you have questions, even over the weekend. And after this assignment is completely graded, my goal is to grade it as soon as I can on Friday, try not to get into Saturday, and I'll scan your responses and send them back to you so that you'll have that extra resource to study while you're over the weekend. So that's our plan going forward. Any questions at the moment, folks? Okay, well, let's jump into our current section on 3.8. In 3.8, we left off on this problem right here. I put all this here just as a reminder, so I didn't scroll past it. And let's also remind ourselves what's going on. It's kind of rough coming back to a problem that was broken in half over a couple class days. So we're dealing with strontium-90. Its half-life was 28 days. And once we discovered the half-life, we found its relative decay rate essentially instantly. We just plugged it in the denominator using this formula here. So the initial mass was provided, essentially K was provided in a roundabout way. We automatically had a mass function. We want to know the mass at 40 days, and it came out to 18.57 milligrams. Then we want to know how long does it take for the sample to decay to 2 milligrams, starting from 50. We looked through that and found it took 130.03 days. But the last thing we want to answer, this is the new part of the problem in red. After 130.03 days, approximately, really that's the exact figure here, we want to know what rate is the sample decaying at that time. So the idea with this, we have the actual mass equation. It's right above, written this way, but that's not what we want. If they're asking what rate is it decaying, the word rate is telling us we're doing this right here. We're working with the actual derivative. So we'll begin by saying, at this time, the rate of decay is, we'll write down the differential equation, dm dt. We're evaluating it at a certain time. That's going to be the 130.03 days. So let's say evaluated at 130.03 days. And the output is going to turn into K times the amount of mass after 130.03 days. So that's our evaluation right there. The good news is we don't actually have to calculate mass at 130.03 days because we know the answer. It said, how long does it take the sample to decay to 2 milligrams? That was that time figure. So we can just reverse it and say at that amount of time, we get a mass of 2 grams, which we're putting right here. So let's use a color just to connect that. Mass at 130.03 days is the 2 milligrams that we solved for. So we're just going to put 2 milligrams right there. We still need the K value. I have completely forgotten what that was. So let me scroll up for one moment. K was natural log 2 divided by 28. So equals natural log 2 negative of natural log 2 divided by 28 is now multiplying 2 milligrams. So it'll be in units of mass in milligrams per day per time. So whatever that figure comes out to, we're in great shape. You know, this one's not a bad one, since if you gave me this as an answer, a negative natural log 2 divided by 14 milligrams per day, then I would absolutely consider that full credit right away. You have the exact figure. That's kind of nice. And even if you made a mistake in the calculator, I would just circle this and check mark it. I would give that full credit. But honestly, it's still kind of interesting to see what is the actual figure. It's down to a measly 2 milligrams. Its half-life is 28 days. So it's kind of interesting to see what this comes out as. Let's actually calculate it regardless. So back up here, this will be negative natural log 2, divide by 14. And we're shown that's going to be decaying at a rate of negative 0.04951 milligrams per day. Negative 0.0491 milligrams per day. But that's only at the 130.03 day mark. If we asked it same question at 150 days, now we would actually have to calculate mass at 150 days. And this, well, it's still going to be negative, but it'll be a smaller amount. It's losing less and less as time goes by, but it's always going to have this negative decay rate. Well, that's the conclusion on this problem here, folks. Sorry for breaking this over a Monday to a Wednesday class. Any questions at all in getting through this one? Okay, so I guess the big reminder on any one of these kinds of problems is that it's not always just about the equation solution, this mass of t function. The actual derivative right here, the original differential equation, is equally important whenever we're dealing with exponential growth and exponential decay. So what we're going to be doing next is extending this kind of work to Newton's law of cooling. Newton's law of cooling gives us a completely different differential equation. The wording says, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference of the object and its surroundings. So let's stop right here. When it said the rate of cooling, that's this. T is going to be temperature. Lowercase t is time. That's kind of awkward. So think of uppercase T as temperature. This is the rate of cooling right here. Is proportional, they say next. Well, K is our proportionality constant. And just like before, even though it's called Newton's law of cooling, things could be cooling down or warming up. If things are cooling down, K is negative. If things are warming up, K would be positive. So it's proportional to the temperature difference between the object, that's T, the temperature of the object at time T, and its surrounding. That's TS right here. So there's really a lot of things going on with this differential equation. Let's list them out just for the sake of notes. T of T is temperature. T sub S is surrounding temperature. You can think of it as, say, ambient temperature. And K, well, we'll call this the relative growth or decay rate. I'll call it just decay rate. Relative decay rate. I want a P here for temperature. That seems like the right thing to do. So the surrounding temperature, we're going to think of that as being constant. Same with the K value, the relative decay rate or growth rate. In the prior problems, that one was also constant. So these two will be constants whenever we differentiate. So now our author discusses how you would even solve that differential equation. Not the most fair problem because, once again, it's not really a class on differential equations. He makes a substitution and he calls t minus ts a new function y. If that's a new function y, it becomes this by that substitution. He solves it, gets this to come out, and then he undoes the substitution. Where the y is right here, it becomes t minus ts. So he adds t sub s to the right-hand side. So there it is, t sub s on the right-hand side. That's going to be the solution right here. When it comes to Newton's law of cooling, the differential equation and the solution, these are all of the possible solutions to that. Just like before, both of those are equally as important in formulas. So that's the full statement of the problem. It's a little bit rough because it feels like a lot is going on. But if you take the extra time on the extra setup we'll be putting in, the organization of the problem, it'll feel like we're doing like example 2, just a couple little tweaks. Any questions, folks, before we start this out? Okay, so here's the first thing we got to do. When you read a sentence like this, I would read it, reread it, and reread it because there's a lot going on in that. It starts off by saying a thermometer is taken from a room where the temperature is 20 degrees to the outdoors where the temperature is 5 degrees. Let's kind of slow this down. A thermometer is taken from a room where the temperature is 20 degrees. So we'll say, actually, I want to use this color here. Temperature at some time is 20 degrees Celsius. Anyone see what the time is right here? That would be implied. Exactly. We're thinking of time 0 starting the minute the thermometer is placed into a new location. So the initial temperature, 20 degrees. Then we're taking it to a new environment, to the outdoors, where the temperature is 5 degrees. That's our ambient temperature. So I'll call that T sub S. For surrounding temperature is 5 degrees Celsius. So obviously the thermometer is going to drop. And if you want to discover and start modeling how the temperature drops, you need a data point. It says right here, after 1 minute, the thermometer reads 12 degrees Celsius. That's our data point right here. We'll say temperature at 1 minute, it dropped 8 degrees. That's kind of substantial. It comes out as 12 degrees Celsius altogether. So they gave us 3 different values to work with. That's kind of nice. Now, here's the question. What will the reading on the thermometer be after 1 minute? So I'm going to write this here. Temperature at 2 equals, and just put a question mark. This is my way of coming back to this because once we put down a number here, all of our work is done. That's the whole question of the problem, at least as far as part A is concerned. Now, we have 2 things on the table for us. We have the derivative right here. We have the temperature function. And, well, I'm not sure how we could use the derivative. They never actually gave us a rate at the moment. So instead, let's begin with this temperature function right here. We can begin by writing out temperature at time t is going to be, first, we put in the initial temperature. That one we found to be 20 degrees. So 20 degrees will go here. Actually, I'll drop the units at this stage just to clean it up. We'll focus on the algebra. Subtract the surrounding temperature, so minus 5 degrees. Is equal to e to the power of, we can't do anything with k. T is the independent variable, so it has to stay as a t. Then we go and add the surrounding temperature to the right-hand side. So plus 5 degrees would go right here. So that's our temperature function. It'll clean up a little bit. We could call this temperature at time t is 15 e to the power kt plus 5. So now that we have that, well, we can use this information. This was the one data point they supplied to us that being 1 minute in the outdoors, we had 12 degrees as a reading. Here's the temperature at any time. So we can now say temperature 1 minute later. All we're going to do is put 1 minute right where the time variable is right here. It'll give us 15 e to the k times 1 plus 5. So the right-hand side is just the outputs to this function. Our left-hand side, temperature at 1 minute, we can throw in those 12 degrees right here. That means we have an equation on the table. 12 degrees is now equal to 15 e to the k plus 5. From here, we can solve for the k value. We'll plug it in right here once we have it. Any questions to this stage so far? Yeah.
Would we redo the function for when it's 1 minute and replace the 20 with the, well,
Replace, you were saying replace this 20.
yeah, replace that function with the 12.
If we put a 12 right here, you're saying,
Yeah.
we would be putting it into that location is the trouble.
Oh.
And that location, we have to have the initial, yeah.
Okay.
Other questions at the moment? Yeah,
Kind of similar to that question, why do we have to do temperature at ×1? Why can't we do it temperature at ×0? Why can't we put that in?
we absolutely could plug in 0. If we plugged in temperature at 0, what would happen is we get a 0 right here for the t value. So it's 15 e to the power of 0 plus 5. Then that would give us a 15 plus 5. But that would just give us back our original information that temperature at 0 is 20 degrees. What's that? Yeah, only reason is plugging in 0 wipes out our k value right there. Other questions so far? Well, these are very, very good questions. And to me, again, that's what makes Newton's law of cooling a little bit trickier. There's more information that we have to stitch together to get to the function right here. And now using this value, there's really 4 different things. Well, in a sense, there's the initial temperature, there's the surrounding temperature that goes into 2 places, and now there's the k value that we have to solve for as well. So really 3 big things: initial, surrounding. Once we get k, we'll be able to say what temperature at time 2 is right away. Other questions so far? Okay, so we plugged in the 1 inside our function. That's not quite done. It leaves k standing, and temperature at 1 is 12 degrees, so we stuck that right here. So now we can start solving for k. Subtract 5 from both sides, and we get that, well, that's the eraser tool. 7 is equal to 15 e to the power of k. Divide by 15 on both sides, and now we have 7/15 equals e to the power of k. And our big trick at this step, just take the natural log of both sides. The moment you do that, you get natural log 7/15. Natural log of e to the power of k just gives you k back, canceling off the base e exponential. So now with k in play, we can come back to our temperature function and say, temperature at time t is finally found to be 15 e to the power of, k is this natural log of 7/15, so I'll just put a t right in front of it. So natural log 7/15. And here's why I said in front, but I guess it can go right here. I ran out of space in front. It doesn't matter, multiplication is commutative. And then plus 5. So now we have the temperature function. Essentially, all we did was went to the formula up here, highlighted in yellow. You know, it might help to re-highlight this. We put temperature of 0 here, surrounding temperature here, surrounding temperature here, and the k rate, k went to that location. That allows us finally to go back to the question of the problem. They asked, well, after 1 minute, the temperature dropped to 12 degrees. 1 minute later, any guesses on how cold it'll be at that point? Kind of hard to guess. It dropped 8 first. If it was linear, it would drop 8 again, right? And take this down to, sorry, say again? Something like that. Yeah, I really have no idea. It's probably not linear because we have an exponential right here. So we're gonna have to just see and find out. Let's calculate temperature at time 2. It dropped fast at first. It can't drop fast forever. The temperatures would become negative pretty quickly. But at a 2 value, we'll get 15 e to the power natural log of 7/15 times 2 plus 5. And with the exam looming, this is not on exam 2, but it would be on the 3rd exam. I've been thinking about the calculator policy. Calculators are allowed on exams as long as they're not a graphing calculator. If this was a real exam 3 question, and you put this down, I don't think I would take off credit, even if you got it wrong in the calculator. I feel like this is a pretty good answer as it stands. Still, it's nice to have a calculator. It's a good idea to calculate on the exam because if that turned out to be, say, 30 degrees, we're way off base, right? That's impossible. But if you have this as an exact form on your exam, maybe you're running low on time, you can skip actually calculating it. I would be okay with that. On our homework, we really ought to, since we have the time to practice those kinds of things. But in this calculator, it'll come in as a 15 e to the power of natural log, 7 divided by 15, times 2. Oh, that didn't work. It has to be times 2 up here. When I hit times, it goes down. Let me try one more time. To put it right here ought to work. There we go. It's just being picky. Times 2 here, plus 5. Took us to about, if we're rounding, let's say 8.3 degrees. So 8.3 degrees Celsius. It definitely dropped, but to me, the kind of the surprise on this is it really didn't drop as much, right? It drops a lot fast, but then its rate of dropping temperature is starting to slow down. We could get a feel for if that really should be the case by just plotting the whole function. Temperature at time t is 15 e to the power t times, oh, let's doing that again, natural log 7/15 plus 5 gives us this kind of graph. Initial temperature is right here at 20 degrees. At 1 minute, see if we can get it to a 1 minute, it dropped down to 12 degrees, but it looks like when it keeps on dropping, it's slowing down. It's approaching a horizontal asymptote. That horizontal asymptote ought to be the surrounding temperature of 5 degrees Celsius. So it's going to approach it extremely fast at first, but then it sort of levels off. There'll be little change once you're around the 5-minute mark. Well, we did it, folks. That's what happens with a thermometer. Really, we used the exponential decay formula. Our author himself did a substitution on the new differential equation, giving us that solution. And same kind of work got us right here. We have a follow-up question. We want to know when will the thermometer read 6 degrees? And then we'll try the problem right after this one. First, any questions or comments at the moment? Okay, the follow-up question, really, it's not too bad. The hardest stuff, usually for every one of these problems, is really right here, building out that function entirely. That's where most of the fighting is typically happening in these kinds of problems. For a follow-up question like this one, it asks, when will the temperature read 6 degrees? So we can write it out like this. Temperature at time t equals 6 degrees Celsius. The moment we do that, we can go back up and substitute temperature at time t for that full equation. It's 15 e to the natural log 7/15 times t plus 5 equals 6. So that's our equation to solve. Really fast, actually. Subtract 5 from both sides, divide by 15, and you'll get this as a result. E to the natural log 7/15 times t equals, first I'm subtracting 5, so this becomes a 1. Then I'm dividing by the 15, so we're now up to 1/15. I'm also running out of space, so I'll use this arrow trick to get some more vertical space going. So that's our value so far. Take the natural log of both sides, and you will get, on the left-hand side, natural log 7/15 times t, and on the right-hand side, it'll be natural log of 1/15. So that step right there makes sense to folks on taking the natural logs. Awesome, glad to hear that. Oftentimes, it's not a bad idea to do it this way in your work. Really, this is what we did. We took the natural log on the left, natural log on the right, and that implied a cancellation. But if you feel like you've just done that so many times, you want to follow the arrow and just write out like this right away, that's okay too. Either way, last thing we have to do is divide by t. So t would be equal to the natural log of a 15 divided by the natural log of 7/15. We now are ready to get a time value out for this. Make Desmos a little bit more manageable. We were gunning for 6 degrees, so if we try to do it graphically, it's really, really hard. But if we tried, let's see here, we at least get a set of expectations. I'm expecting about 3.6 minutes. We still have to show the algebra, but now we'll see if this answer is even reasonable. Natural log of a 15 divide by natural log of 7/15 gives us 3.55 minutes. That tells us especially with the graph, we have overwhelming numerical evidence. The algebra down here is accurate. Let's say our answer is, say, 3.6 minutes. So we did it, folks. We have the full function. We've solved for the K value to get it. Now we can find the temperature at any specific time, or do these scenarios, find the time when it reaches any level of temperature. Well, any questions, folks, on the conclusion here? Okay, well, let's try it again. The one thing we didn't do on this problem, the reason there's another question here, is we didn't use that formula, the one highlighted above. And I mentioned they're both equally important. Let's bring that back just to emphasize. So let's try out a problem where you had to have this to really get through it at all. That's example 5. Example 5 says, I believe there's one very similar in the homework as well. A freshly brewed thermos full of coffee has temperature 98 degrees Celsius. That definitely sounds like it's scalding in an 18 degrees Celsius room. When its temperature is 90 degrees, it's cooling at a rate of a half a degree Celsius per minute. Now, I don't know what kind of fancy lab equipment people have in their office to measure the rate of cooling of their coffee thermos, but supposing they have that, we can find out the time it made it to 90 degrees. So that's what our goal is on this problem here. Now, it's all about organization. So if you see this problem, here's the first thing I would put down even before considering this information. Let's put down the differential equation. Rate of change of temperature with respect to time is the constant of proportionality K times the difference of temperature and the surrounding environment temperature. So that's our underlying differential equation that governs everything. And this equation is intricately tied to its solution, which goes temperature at time t equals an initial temperature minus a surrounding temperature, and I want to keep this color coding the same. Then that's multiplied by e to the power of the decay constant K times T. And this is the step I always forget. Because a substitution was being made, it had to be undone, and the algebra there gave us plus surrounding temperature again. So that's our full equation. We need both of them to get through this problem. Now let's read through the problem and see just what's going on. So we have a value of 98 degrees Celsius, but when they said freshly brewed, they were hinting at us that that's an initial value right here. The initial temperature, T of 0, is 98 degrees Celsius. Then it says, we took it to an 18 degrees Celsius room, so that's going to be surrounding temperature. So T sub S for surrounding temperature is 18 degrees Celsius. Next it says, when its temperature is 90 degrees, it is cooling at a rate of a half a degree Celsius per minute. That's a heck of a statement. We want to know, when does this occur? So that's essentially the question, a time value. So to go through this one, I want to do something a little bit unusual that we haven't really done in the notes before. They're asking me for a time value. Oh, I didn't mean to scribble. They're asking us for a time value. And I don't want to use that at just a T for that. Reason being, it would be conflated with these T's here and here. We don't want that kind of conflict. So instead, I'm going to write this out. Let T equal T naught. That's the unknown temperature. That's going to be the question we try to solve. So when T is equal to T naught, and this is minutes, let's read out this sentence again. The temperature is 90 degrees Celsius. That's just a function evaluation. They just straight out said temperature, so T, at that time, T naught, is 90 degrees Celsius. And then they said a little bit more, actually a heck of a lot more. They said also, it is cooling at a rate of a half a degree Celsius per minute. When they said rate right there, that's the derivative. So we'll write out the derivative of temperature with respect to time This happens at T naught, so we need to evaluate it at time equals T naught. Is cooling at a rate of a half a degree Celsius per minute. What I'm about to write down is wrong, but let me know if you can see where the error is. A half a degree Celsius per minute. The units are actually okay, but there's something missing on this equation. Yeah, go ahead. Exactly. There's a negative that's implied here. Super, super easy to miss, especially if you're reading through it really fast. When it says cooling at a rate of a half a degree Celsius per minute, it implies the derivative is negative right there. So watch out for those. I really kind of hate that, but it's just a side effect of if you're putting this in ordinary words, you'd replace the negative with a word like this, cooling. I think that's an adverb. Let me know if that's wrong. Well, we have all of our information. We started with the formulas. We just dumped them on the page. This is the supplied information. And now the whole question is, what is T naught? Sometimes for tricky problems like this, it's not a bad idea to rephrase this. We need to solve for T naught. So that's our end goal here. Well, how can we do it? We could write down this temperature at time T function. We know what T of 0 is. We know what the surrounding temperature is, but we don't know K at all. And let's think, how did we get K? We got K by plugging in a known data value like this one. At 1 minute, it was 12 degrees later. That was enough for us to solve for K immediately. But we don't have a data value on this one. Well, we kind of do, but it's for the derivative. It's not for the underlying function. So the strategy I used before is just not going to work. Instead, if they gave us a derivative value, that's probably where we need to start. Let's begin by just using this derivative. Note, we don't have to calculate it. The derivative of this function is automatically that format. So let's start with this right here. We'll start to just say this is the setup or start of the problem. We can take dt, or better said, the rate of change of temperature with respect to time. It's still going to be evaluated when the temperature is equal to T naught. When we do that, we're going to get our K value right here. I'm pretty much just copying this equation of above. When you get to T, the input has been suppressed. But if you're passing an input T equals T naught, we would write it this way. Temperature at T naught. Then subtract the surrounding temperature, so it's going to be minus. We do know the surrounding temperature to be 18 degrees Celsius. So they supply this information about the derivative. All I've done is put in T equals T naught inside that derivative. So that's our right-hand side. But the left-hand side is negative 1/2. So we now have an equation, folks. We have negative 1/2 on the left-hand side, K times a bunch of stuff on the right-hand side. And it's not too bad to evaluate. I mean, we already know that there's a minus 18. But it's kind of easy to get in a loop with this information because there's a lot of information. Anyone recall what temperature at T naught has to be? Exactly, that came out as right here, 90 degrees. Oh, better right here. I even highlighted it. 90 degrees right here goes into that position. So this is becoming more and more like an equation where you could solve for K on. Let's subtract 18 here. Negative 1/2 equals, I want to keep that blue. So let me just hit it with the highlighter. And now this is going to be 72. Divide both sides by 72. And the decay rate K is negative 1/144. So now that we have K, we are set up. We're going to throw it to right there, and that's going to give us our temperature function completely written out. But first, any questions, folks, to get to that point of the work? Okay, last thing to write out then, well, not last thing, but next thing to write out is all of this implies finally that the temperature at any time T, so not a T naught just yet, is going to be T naught minus Ts. So T at 0 or T naught is 98 degrees. My surrounding temperature of 18 degrees. So we'll have two things substituted right here. Right where E is, we'll go e to the power. K is -1/44, so I'll write it like this. -1 times T, so just T, divide by 144. Then last substitution, the TS here becomes 18 degrees Celsius. So one more step to take, temperature at any time T, finally after small simplification looks like 80 e to the power of -T divided by 144 plus 18. So this will tell us the temperature at any time whatsoever. Took a lot of work to get to that stage. Any questions, folks, on the steps we took? Yeah, go ahead.
So the reason why you use T naught instead of TS, your position originally, is because T naught is giving you a value that has to be rate of change, right?
Exactly.
At that point.
Exactly, yes. Yeah. And also the T naught right here is going to help us avoid putting things like a T here when we really meant a specific value giving the 90 degrees. Other questions so far? Okay. The best case would be if we had like a number here, like 10, we would have plugged it in here and in here. But if they gave us this as a question and we're solving for it, it's sometimes a little bit helpful to just set it up as a new quantity in that kind of way, a new variable essentially. So let's see, have we solved the question? Doesn't look like it, right? The solution to the question is to know at what time T naught, we need to solve for T naught, we set as a reminder, the temperature came down to 90 degrees so that it was cooling at 0.5 degree Celsius per minute. I can't find the temp time in this formula at all. I mean, there's no times I could put in, but we can with this one right here. So now we're going back to this. At time T naught, we got to 90 degrees. We're going to plug that in right here, temperature at T naught. So here is the last steps of this solution. I'll put here, finally, just to organize the steps we're taking on this work. If temperature at time T naught is 90 degrees Celsius, then right where we see temperature at time T naught, we'll just replace that T with the T naught. It becomes 80 e to the power of -T naught, divide by 144, plus 18. I often forget the plus 18 because it's so unusual. It only happens in Newton's law of cooling. And it's set equal to 90 degrees Celsius. And we've done these kinds of equations before. This is like our 4th or 5th one on these notes, so it's not too bad. Subtract 18 from both sides. And we will get, let's see, 72 on the right-hand side. Divide both sides by 80, and we get e -T naught. If I should scroll just a little bit more, over 144 equals, I feel like 72 over 80 should reduce. 8 goes in the numerator 9 times, denominator 10 times. So we get 9/10 there. Finally, take natural log of both sides. Natural log kills the base E exponential on the left, so it's just a -T naught. Divide by 144. On the right-hand side, it stays as natural log 9/10. And then last bit of scrolling, multiply both sides by -144. And we have now T naught equals -144 natural log 9/10. So whatever that comes out as, that's going to be our time. Like I mentioned before, on a homework, we really ought to calculate this. I mean, it's a good idea. If it came out negative, it's the wrong answer. On an exam setting, if you ran out of time, I would give the exact expression here, which you would get to going through the algebra anyway. I would give that full credit. So back to Desmos, let's see what this comes out as and see if it's even reasonable. -144 natural log 9/10 comes out as, I believe this was in minutes, which would say 15 minutes. this is in hours we're in trouble, right? It shouldn't take 15 hours to drop the temperature by 8 degrees. Let's double check the unit here. Half a degree Celsius per minute. That now makes it seem reasonable. Dropping from 98 degrees to 90 degrees in a time frame of 15 minutes, I would absolutely believe that. It's still scalding 15 minutes later. Let's call it maybe 15.2 minutes. Seems reasonable to round. I mean, if people are really interested in this problem, we could give them 15.17 minutes, but in all practicality, that's probably just as accurate for them if it's just coffee. Well, any questions, folks, on getting through this one? Okay, well, that's the last of this section on exponential growth and decay. Essentially, what we're going to do now is turn to our last application section in chapter 3. After that, after our second exam, still 2 more sections to get through in chapter 3, but they're not so bad. It's kind of, we're over the hump at this point. Well, close to it. So last section is 3.9. And we'll be finishing 3.9 on our Thursday's class. These are longer sections, so we're breaking them up over an extra day. But just a word of warning, for a lot of people, I felt this way myself when I was a student. This section is very, very infamous. It's just complicated. There's a lot going on. But the main thing that you need to get through related rates is think of all your training in implicit differentiation. It's going to be that kind of stuff happening. But when we differentiated implicitly, the assumption was that x was a function of y. Here it's a little bit different. Both variables you see here, both the x and y are functions of time. That means when we go to differentiate, chain rule is everywhere. The derivative of x squared, that's going to be a product rule, but if it was an x squared plus y cubed, derivative of x squared is not 2x anymore when they say x and y are both functions of time. So suddenly, we need to be very, very particular about what is x and y really. If they say they're both functions of time, I'll sometimes write this on the paper just as a reminder. X is really a function of time. I don't know what it is. It's completely unknown to us. Y is also a different function of time. So g of t, it's also unknown, but they're all related through this equation right here. Some way, somehow, we can relate those functions. So that's our setup so far. If you take this curve, plot into Desmos, this is what it produces. You can solve for y exactly on this one. So that's why it does pass the vertical line test. It's not as weird as like we saw in our implicit differentiation section. And the first question asks, if dy dt is 1/2 meters per second and x equals 2 meters, which horizontal direction is the particle moving in? That just sounds completely mysterious to me. But let me give you some hints on how to think about this one. I kind of shouldn't have closed 3.8 too early. Folks in the class made a really, really important observation. Right here, when you saw that it was cooling, you knew to put a negative in the derivative. That's extremely important. If the derivative is positive, something is going in the positive direction. If the derivative is negative, something is going in the negative direction instead. If you keep those two ideas completely together, it helps out right here. So here's how we're going to analyze this. We have a derivative for the y function. All we know is it's 1/2 meters per second when x is at 2 meters. Let's put that 2 meters as a dot right here. Now they're asking the question, is that dot as a horizontal direction? Is it moving, say, to the right? I'll put a question mark there because we're uncertain. Or is it moving to the left? I mean, it doesn't really move to the left. It goes upward. It has to follow this track. But if we're just thinking horizontal, is it moving leftwards or rightwards is the question. But that's positive. It's the rate of change of the second coordinate y. At any point here, we have an xy. And if the derivative of y with respect to time came out as positive, is the y coordinate going up or is it going down? Exactly. A positive means it's going in the positive direction. For a second coordinate, it means it's going up. So if that point is going up, which direction is it really going, left or right? Exactly. If you force this point to go up, that means it's going in this direction towards the left. Kind of weird, right? It was all about that sign right there. So let's write this out. Since dy dt is positive, the y-coordinate is increasing. Let's go back to the graph. Oh, didn't mean to scribble on it. Let's go back to the graph. We're at a position 2 right here, and it must be going up. That means right here at 2, once again, where x is 2 meters, its horizontal position is going this way off to the left. So we'll say x is moving, or we could say x, but it's better to say the particle. That would be this point right here. The particle is moving to the left. If this coordinate was negative instead, the arrow here in orange would have been pointing down, and that means the dot is moving to the right in that other direction. Definitely kind of weird, but we're going to be practicing this more and more as we get through this notes. It already came up once in section 3.8. Any questions at all about that assessment there? Okay, now part B is asking us the following. What is the rate? That's a derivative now, at which the x-coordinate of the position particle changing when dy dt is a half and x equals 2. So we're keeping the same derivative right here. We're keeping the same position on x. We knew that the y-coordinate is increasing at a rate of 1/2 meters per second. But over here, we want to know the rates are related. What is the rate at which the x-coordinate is changing? So here's the question essentially. When it said, what is the rate? It's saying dx dt, the rate of change of the x-coordinate with respect to time. That looks so weird because we're used to thinking of x as a variable, but x is not just a variable here, it's a bona fide function itself. So that's an appropriate notation. So we want to solve what dx dt is equal to. When x equals 2 and dy dt is a half. If we can find that value, we're done. There's a small check inside of this though. Are we expecting a positive value or a negative value for dx dt? Turns out it wouldn't be positive on this particular case. It's negative, but it's hard to see why sometimes. It's kind of essentially what we did over here. When we said dy dt is positive, that means the y function should be moving in the positive direction. It should be increasing. But we said x is moving now towards the left, going this way. That means it's going towards the negative direction. X is decreasing. So whatever dx dt comes out as, only because it's moving to the left, we're expecting negative. So let's say right here, since the particle is moving to the left, this quantity, dx dt, think of the green arrow that we put right there. We still have to calculate it, but at least we do know that's a negative value. So those are the ideas that are going to help us get through this problem. It was a lot of analysis before we even got started, but now we need to turn to this equation, which is plotted as the red curve, start differentiating it with the goal of solving for dx dt. Any questions at all, folks, before we start it up? Okay, so back to this equation here. I'm going to recopy it down. X squared y cubed equals 4/27. So here's x squared y cubed. I'll put parentheses around it because we're about to do something to it, equals 4/27 with a little bit of space, and parentheses don't hurt. And it's just like you're in the section on implicit differentiation. We are differentiating both sides of this equation, but the derivative we're taking is with respect to time. So we're doing d dt on the left, d dt on the right. You could call it a prime here, not using the d dt, a prime here as well. But in these contexts where there's three variables really, an x variable, a y variable, and a third time variable, Leibniz notation becomes really, really vital to say exactly what you're really doing. Otherwise, it's ambiguous. It's hard to tell what a prime would even mean at this stage. So let's go take this derivative. The right-hand side's great. It's just 0, right? It's just a constant. That rule still applies. But the left-hand side has to start with the product rule. We have two functions of time. So the product rule is going to come down as, I'll differentiate one first, copy the other one, then copy the other, and differentiate the other. I wrote this in a slightly different format because typically if you're using Leibniz notation, you want the ddt to be on the right for both of them. Otherwise, it's easy to mix up what's being differentiated really. But it's still the same kind of game here. If you had x squared, we can copy it on this one. And then I have to copy it over here just to make sure I differentiate it. If you have a y cubed, well, you can copy your y cubed here. You're differentiating that one. But over here, it's undifferentiated, so it just copies in. And the right-hand side, that's the easy derivative, comes out as 0 since we're differentiating a constant. So that's where it settles at so far. I haven't taken the derivative of the y cubed or the x squared, but we're starting the derivative. That's how the product rule begins. Any questions to that stage? Okay, let's run through this next stage really, really slowly. X squared is being copied, so there it is. But once you get to y cubed, we're differentiating implicitly. Y is an implicit function of time. I don't even know the function, but it's still really just the chain rule. Anyone know what the outer function should be? Exactly, the power 3 is the outer one. We'll do that first. And the function y, that's the one that's inner. We'll do second. So our trading in the chain rule still is an effect on this. That's finally what makes chain rule tricky. It shows up everywhere, calculus 1, 2, and 3, in many, many different kinds of forms. But it's still the idea of a function composition. So running through this derivative will look like this. Let's actually kind of, though I've already used that color, I think we're okay to just keep it black. Let's go and say times. Take the derivative of the outer function first. It'll essentially look like this. 3 and y gets taken to the power of 2. Then we multiply by the derivative of the inner function. I wouldn't want to call that a y prime. The better format would be dy dt. So that's our first run through on that derivative there. Does that make sense to folks on getting that output? Awesome. Really the same kind of thing we did in implicit differentiation. Every time we differentiate something relative to y, if it was like a power 3, we would get 3y squared times dy dt. Then we go plus, y cubed carries in, and ordinarily you would call this 2x, but not here. This depends on the context. Up by the red dot, we are known that x is also a function of time. So that tells us this further information that the power 2 here is now an outer function, and x, which is really f of t for some unknown function f, that's the inner function 2. So differentiating this one will become, we copied our y cubed, 2 comes down for x. The new power was 1, so I'll just leave it as an x. The chain rule says, now multiply by the derivative of the inner function. That will be a times dx dt. And the whole thing is set equal to 0. What was our goal? It said, what is the rate at which the x coordinate is changing when dy dt is a half and x is 2? Well, x is 2 means we can plug a 2 here and here. That's kind of nice. Dy dt being a half, we can plug that right here. And the whole question is dx dt. We need to solve for that to get an answer out. But notice what's missing. I don't have a value for y yet. But it's okay. X and y are definitely related. They're related through that equation. So it was kind of rude. They only gave us the x value. We have to find the y value ourselves. So I'm going to copy that equation down. X squared times y cubed is 4/27. And where can we fit it? I'll have to work out here. X squared y cubed equals 4/27. So let's plug in our value for x. When x is 2, this is going to become a 2 squared. Y cubed is still here, equals 4/27. The 2 squared is going to become a 4. So we now have 4y cubed is 4/27. Let's hide that example 2 for the moment. Divide both sides by 4, and y cubed is 1/27. And I officially ran out of space, so follow the arrow. Last step. Take the cube root of both sides, and y equals 1/3 exactly. So we have a value of 1/3 here. Let's double check that. If you put a 2 here, that's 4. 1/3 cubed is a 27. Yeah, that would equate to 4/27 altogether. So we need to take all that information, plug it inside here. I'm sensing we are not going to finish this one. So I'll just put an arrow here for the notes, just to make it readable. It continues. My goal is to not have to do that too often, but here's our continues onto the next page problem. All we're doing now is making substitutions everywhere where it's highlighted. So in place of x squared, we're going to plug a 2. It becomes 2 squared times 3 times y squared. That's going to be a 1/9 in the end. So 1/3 first goes in, plus our y cubed now. That's a 3rd cubed times 2 times the value for x. We're back to a 2 for x. Oh, sorry, folks. I need to back up just a little bit. Apologies to everyone working in pen. I was doing really great until I skipped over this one, didn't I? That one is a value of a half. We need to throw that in. So times 1/2. It's kind of terrible to be okay on the algebra, or excuse me, the calculus, which is nasty, but go too fast in the algebra and make a mistake there. That's kind of unsatisfying. So let's now go plus. We have y cubed, so that's a 3rd cube. It's times 2 times x, that's where we left off. We look up the value for x, which is a 2 up there. And then dx dt, that's what we're solving for. Good news, that is an equation you can solve for dx dt on. But remember, dx dt had better be negative, whatever we come up with. So if we don't get that right sign, well, we'll be back to the drawing board on this one. So let's hope we get it down. At this stage, it's just cranking it out. This is going to be 4 times 3 times a 9th. I'm going to write this as 4 times 3 times 1/9 times 1/2. Over here, we have a 27 times through here, we have a 4. And then dx dt. Still set equal to 0. But before we get too involved, we can do cancellations over here. This 2 can cancel into the 4, leaving a 2. That's going to be hard to remember there's a 2 there. Let me do it like this for that cancellation. This 3 will cancel into the 9, leaving a 3 down below. I forgot to put my 0 on the right-hand side, so let's put that in. So this first term right here looks like it's a glorified 2/3, not too bad. Plus, over here it's a 4/27 dx dt. Now let's subtract 2/3. 4/27 of dx dt is now -2/3. And hey, that's good. That's our negative that we're expecting. We're going to multiply by a positive quantity, 27/4 on both sides. Which means more cancellations. 3 goes into this 27 9 times. This 2 cancels into the 4, going in twice. That negative sign is still alive. And we now have, after hiding the Boyle's Law problem again, let's just stick it way down there, dx dt equals -9/2 meters per second. So our dy dt, if the y coordinate is going up by a rate of 1/2 meters per second, the x coordinate is flying. It's going left at a starting rate of -9/2 meters per second. Would that make sense? Let's take a look. If you're right here on the curve, going up by a tiny amount means you have to go left by a large amount. So I would absolutely believe that our derivative going to the left should be larger in magnitude than the derivative for the one going upwards being 1/2. So we've got it, folks. That's what related rates looks like. It's a jumbled mess, unfortunately, because when you're dealing with related rates, there is often a third variable or multiple functions all over the place that we have to work out, identify, and be really, really careful with the chain rule, implicit differentiation, as we go to calculate. Well, I think this is probably a good stopping point for us, folks. The Boyle's Law we'll do next on Thursday's class. Takes a little bit longer to go through. Any last questions before we call it a night today? Okay, well, have a great night, folks. And, oh, sorry, question first.
Oh, no, the y coordinate goes up by 1/2, x is down by -9/2.
Exactly. So we're going up by 0.5 meters per second over here, but going left by 9.5 meters per second going that way. And the negative just means going to the left.
Oh, no, yeah.